So, we're going to continue on the course, of course, algebraic femboid topology, by discussing first a mistake that I committed in a previous lecture, notably the one with fundamental groups, and the first time I constructed them. Okay, so previously, what I mentioned was that the fundamental group of the femboid torus, FT2, I know I use this notation, FT2, I use blackboard bold, but these two are just one and the same, okay, notation wise. Okay, so, okay, FT2, that is, the fundamental group of this is primarily the free group on two generators, F1, F2, such that F1, F2, F1 inverse, F2 inverse equals 1. Or, it would be this one here, FT2, F1, F2, F1, F2, F1 inverse, F2 inverse equals 0. Okay, the thing why I wrote this down is because there are primarily two versions of the fundamental group, which would be multiplicative and additive. So there are two different, although these two are bijective, they're exactly the same, or they're isomorphic. They're the same on the nose. The distinction here is that one is just sort of implied to be multiplicative, and one's implied to be additive. So they're not precisely that way. The operations here are still loop concatenation, but sort of the expression for the identity is just different. Okay, but they're still the same. So I mentioned this over here, and I made the very wrong mistake of assuming that these two are isomorphic to Z2. And there are two reasons why I'm wrong. Okay? So the first reason is that these two structures, although they are groups, I'm assuming the additive integers here and the multiplicative integers. I think it would just be additive, because if it's multiplicative, it would just be a monoid. However, my point is, in this first mistake I did, is that these two structures are incompatible. Because we're using the elementary notation, or the elementary notion of femboids, which is an abstract entity, right, up in a universal space, which is just mathcal f on its own. And the thing is, there is no inherent correspondence between elements of f and elements of the integers. That is, until we say, or until we actually construct fz, which is the set of all femboids inside f, such that there is a bijection between the given set and z, such that its image under a certain function is inside the integers. So, sort of recall this. I think I already discussed this in a previous lecture. So define to be all femboids fi inside mathcal f, such that there exists a var phi, a map, such that the image of fi under var phi is inside the integers. And the image is in fact I, which is an integer, which we say to be an integer, okay? So until we construct this set over here, fz, there is no inherent association between elements of ft2, which is a subset of f2, okay? Essentially f2 right now. So that's the reason why this is wrong. It's supposed to be fz2, but that's where we get to my second point. And my second point, which is the most important point of this video, or this lecture, or this footnote, is that these two are not isomorphic. Okay? So, let me just make that clear. The fundamental group of FT2 is not isomorphic to the two-dimensional flat Gaussian femboids. Okay, the reason why I'm saying flat is because we will define in a later lecture that the Gaussian integers, right, or the femboid Gaussian integers, which is just basically all complex femboids that are part of Fz, such that the real and imaginary components are part of Fz, are yeah, that's a different space than Fz here. So yeah. So okay, if I just replace this with Fz2, although it would fix my first contention with my previous lectures, it doesn't fix the second one because it's not the case for the isomorphic. Because as I have reviewed my lectures lately and my notes, fundamental groups are not inherently abelian. And I know I ignored that notion in that video wherein I constructed these fundamental groups for the first time. And now it's biting me in the butt. So I'm stating it here right now, it's not isomorphic, okay? So first point is that the regular integers and Ft2 are not, or the fundamental group of Ft2 is not compatible. So it must be Fz2. Alright, we need to have that notion of there being an association here so that we can say that, okay, there are femboids that exist inside or somewhat exist inside the integers or can be indexed by the integers. It's all about indexation, I believe, in the end of the day. I mean, yeah. And of course, there's also FR, but that's for a different, more advanced course or lecture in this course. Okay? So, when we do compute the first fundamental group of Ft2, this is where we stop, okay? Over here, in this free group on two femboids. That's where we stop. Okay, and likewise, the same applies for the fundamental group of Fs1, which is just the free group on a singular femboid. Okay, yeah. Okay, something went wrong in this lecture. Yeah. Okay. Yeah. Yeah, the thing is here. Okay. Yeah, there's nothing wrong. It's still not isomorphic, by the way. I was thinking that it was probably isomorphic, but not. It's this one that's essentially isomorphic, okay? Because we will observe that when we do take its commutation relation, right, and mod the original group by the commutation relation, or the commutator subgroup, right, because the abelianization of G, a group G, recall, is G mod its commutator subgroup, which is essentially every element in G put inside the commutation relation, which is, it could be the group operator, but there could be a separate commutation relation such that when we do take this mod here, flipping or switching the two elements in the binary relation will yield the same result inside G. Okay, so yeah. So we're gonna mod out this fundamental group, right, with its commutator subgroup, which is just F and F. And this would be trivial, right? So the thing is, what I need to make sure, what I need to distinguish from the other space to construct is that this here, the trivial case S1, Fs1, the femboid circle, is the only case among the spaces we've discussed so far wherein its fundamental group is isomorphic to its first homology group, okay? And I know you guys have never heard that term yet in this course yet. And I think I mentioned it before already about homology groups. That's the next step after fundamental groups. And homology groups are somewhat, in a way, you can say at the most basic level, they are an abelianization of fundamental groups. But the thing is, they are not always the same or isomorphic on the nose. Okay. In fact, there is a different way, or there is a more fundamental and more robust way of constructing homology groups rather than just modding out by the commutator subgroup. In fact, there may be cases wherein modding out by the commutator subgroup does not work. So yeah. So the thing is, this is the only case where if we mod it out by the commutator subgroup, it would give us something that's isomorphic to Fz. So this is the only case here where the fundamental group is isomorphic to Fz or any of its tuples or any of its members or relatives, Fz2, Fz3, something like that. This is the only case here, Fs1. Because remember that if you mod out by a point, you mod a certain structure out by a point, it just gives us that structure. So if I mod out R plus with say 0, it just still gives us something that's isomorphic to R plus. Okay? So likewise, this commutator gives us a singular element, or it gives us a singular identity or singular element. So pi 1 of F would be modded out by a singular element E, which is a result of putting this F in itself into the commutator relation. That would just be, of course, isomorphic to pi 1 of F. Okay, so essentially doing this would be nothing, and it would still correspond with Fz here. But the thing is, when we do mod these structures here, so pi 1 of Ft2 by its commutator subgroup, it gives us something else, which is the homology group. Okay. So let me just free out some space. So let's abelianize Ft2 here, and we will generalize the process for any genus N surface, but not just genus N, but any femboid genus N surface. And we will also discuss about N-petal roses, and we will femboize them essentially. I don't think I femboized the N-petal rose when I first constructed these fundamental groups, so yeah, we will femboize them today. So that's sort of the third error I did. I didn't femboize the N-petal rose, so that would make the structure, or although they are a substructure or a subspace of the identification space of our N-hole torus, right? Although they would be like a part of the space we take apart from them in order to find the fundamental group, right, of the total space, they become incompatible because they aren't of the same nature, right? Because inherently speaking, the original space is composed of femboids, but now we're saying we have a petal that's composed of regular loops or points. That doesn't make sense. So yeah, we have to femboize that. So that's going to be for the last part. Okay. So going back, let's mod out pi 1 of Ft2 by its commutator subgroup Ft2 Ft2. Oh wait, sorry. It's supposed to be pi 1. I have to move this. Okay. So that would give us yeah, that would give us something that's much, much different, obviously. And point 2 in today's corrections is a very important one, alright? Extremely important. Okay, so that would give us the first homology group of Ft2. And loosely speaking, I guess this would be our introduction to homology groups, or at least our sort of skimming over it. But we're not directly going to go into them in the next lecture. There are still some additional stuff we need to talk about in fundamental groups before we proceed with homology groups. Because homology groups give a richer story to finding holes inside our spaces. Because that's sort of one of the primary goals in algebraic topology. We're going to use abstract algebra to find holes in a space, right? And because when we find holes in the space, that's when we distinguish one space from another. Because a sphere doesn't have a hole compared to a torus, so that's what separates them from each other, or say that they are not homeomorphic, right? So it's a richer way of saying that some spaces are homeomorphic and some spaces are not homeomorphic. Okay, so, alright. So the notation for this here would still be, it would still be a free group over two generators. Nothing changes when it comes to how many generators generate the group, or how many elements generate the group. But the notation stays rather the same. It is still the free group on an F1 and an F2. And it can still be represented via F1, F2, such that, well, F1, F2, F1 inverse, F2 inverse equals 1. But what is implied here this time is that no matter how many times I shuffle here, no matter however way I travel along the identification space, or along the boundary of the identification space, it does not change the structure of the group of the space. Okay, so I have my identification space over here. So by abelianizing it, what I'm saying is that even though I travel, say, this way first, which is B inverse, and then I go A inverse, B inverse, A inverse, it would not matter. Okay, however way. So yeah. So if I make these first, it doesn't matter. Or if I flip these guys, it doesn't matter. So that's what I mean by making it abelian, right? And of course, the same thing would be for the additive version. Just make it 0, or just make the identity 0. So in the homology group of FT2, it would imply now that it's abelian. It's an abelian group now. So I guess commutative, but that's just another name. I'm saying, but the point is we can switch around the members and it will still result in 1. Okay. And so now this is the case wherein our given group here, free group, is isomorphic to F Z2, because we have two generators here, and Z2 and correspondingly FZ2 is generated via via a pair of integers, or a pair of flat femboy Gaussian femboys. A pair of flat Gaussian femboys. Okay. And alright, so another point that we will add at the end of me stating all these errors is a correspondence that we get in the homology groups. Okay. So I'm sort of giving you guys already a taste of fundamental groups, and I'll just sort of write here on the side that pi 1 of a given space X, path connected of course, mod its commutative subgroup, which is essentially its abelianization, is isomorphic to the first homology group of X. So that's a shortcut, and in fact in femboy mathematics, I believe I used this shortcut to speedrun the computation of the first homology group of the torus, just a regular torus, and then I constructed it from its identification space, or its quotient, right? And then found the fundamental group, and then mod out by its commutative subgroup to yield its homology group. So aside getting the chain complex and then modding out certain kernels and images in that chain complex to obtain the homology group, this is an alternative way of finding the homology group. Though it's not a guaranteed would-all-be-all algorithm for finding the homology group of a space. Okay. All right. So going back here, now would be